Now, a useful fact, if S1 is a surface which isn't closed, but S1 union S2 is for some surface S2, S1 union S2 bounds a solid region E and is oriented outwards, then we can just think of it like this, the sum, right? This is equal to S1 union S2, and using our divergence theorem, we get exactly what we're looking for, which implies the integral we're looking for is just the divergence minus our double integral over S2 f dot ds. This is similar to Green's theorem thinking of our holes. So let's do an example here. We have this f, which is given by this function. Let's compute the flux of f across the surface, which is part of the paraboloid x squared plus y squared plus z equals 2, and it's above the plane z equals 1. So if we think about this, we have our paraboloid that's kind of like here, and we have our z, our x, our y, and it's like this, but it's only the boundary, and we're not talking about the bottom right now. So we don't have a closed surface. We don't have a boundary of a solid part. So what do? Cap this off. We fill in the hole, the bottom, with the surface S2, which, if this is kind of S1, all of that, then S2 would be the circle down here. The disk, sorry. Down here, z equals 1, and x squared plus y squared is less than or equal to 1. So we got our two surfaces. So we give the correct orientation to S2. So it has the continuous normal vector field, and the downward is the downward orientation, right? Sticking out. Then we have S1 is equal to our triple integral minus S2, where E is that solid that we've bounded by S1 union S2. So the divergence of f, if you calculate this, is just going to be 1, which again, really nice, right? Derivative with respect to x, derivative with respect to y, derivative with respect to z. So, and the sum of those. So we calculate our triple integral. You can follow all of these steps, but it's really easy. Once again, we're going to use cylindrical coordinates because we got a circle on the bottom, and I don't want to do it without cylindrical coordinates. Blah, 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 blah. We get pi over 2. All right. So we got the first piece of this puzzle. We got this is equal to pi over 2 minus something. Just got to do that last part. So let's do that last part. We compute the double integral of the surface S2 f dot ds. So let's parameterize it, S2, with r, the vector r, being r cosine theta, r sine of theta, 1, because remember z equals 1, where r can be between 0 and 1, theta can be between 0 and 2 pi. Well, the downward normals, right, is going to be the derivative with respect to r and the derivative with respect to theta, which we've calculated here. And then what we have to do is r theta cross r, which we just get 0, 0 minus r. But we plug in our parameterization into f. We get this funky thing. But the more important part is that when we do our dot, because we parameterized it, there's a 0 here, and zeros in these two components, so the dot product is equal to 0. So therefore, our double integral is over the function 0, so it should just be 0. Thus, our integral, we figured out this was pi over 2, this was 0, and this was pi over 2. As easy as, you guessed it, pi. And that's the divergence theorem, which is just Stokes' theorem in higher dimensions. So have a great day, and I hope you enjoyed multivariable calculus.